This is the Windows talk. No, I'm just kidding. It's Container D. I wanted to go ahead and bring up Derek McGowan. I've never pronounced your name out loud.
Really?
Is that the right way?
Yeah, that's good. All right, hello everyone. So I'm Derek McGowan, software engineer at Docker. I'm also a maintainer of Container D. So today we have a few different speakers. So I'm going to go first. I'm going to talk about the architecture of Container D. Then we have Lantao Leo from Google. He's going to talk about CRI as well as some of Google Cloud's use of Container D. And then we're going to have Phil Estes after that talking about IBM Cloud and Container D. After that, we're going to have a kind of Ask the Maintainers Anything panel up here. So we're not going to have a bunch of questions in between. So if you have questions, kind of, you can ask any of the maintainers at the end. So first off, kind of, if you go to Container D's website, this is what you're going to see as our kind of explanation for what Container D is in a short, one sentence. An industry standard container runtime with an emphasis on simplicity, robustness, and portability. So CNCF, we just graduated in CNCF just a couple months ago. I don't have that cool little picture, but if you went to the keynote, you gotta see it. Container D has a composable architecture. What that means is that basically we've designed Container D around having a bunch of reusable interfaces that can be easily implemented of kind of different low-level pieces. And then we have a client, a pretty smart client on top that will kind of make use of all those different composable parts. Container D has also seen kind of broad support and adoption across different companies. As you'll hear a few today, then there's a few that aren't represented today, but we can talk about kind of some of the different companies that are using Container D today in production. And Linux and Windows support. So today we do have in Container D 1.2, we do have a Windows runtime, but as of the next version of Container D 1.3, we're going to have a newly supported runtime that will kind of support going forward. Right now we don't support the actual Windows runtime, but the Microsoft team has been working on making a pretty good runtime to run underneath Container D. So in 1.2, we also released this kind of first-class support for VM-based runtimes. What that means is we stabilized this Shim API that makes it really easy for VM runtimes to implement something that's more optimized for VMs. So, for example, if you're running on Kubernetes and you have your pods and you want to run multiple containers in a single VM, we have a Shim API that will make it really easy in order to do that. We also have kind of a first-class support for Run C. We have our own Shim implementation for that. And then you'll hear later from Lantao about our CRI support that we have. So this is kind of a high-level picture of Container D's architecture. You can see at the top we have the different platforms that you might be using that support Container D today. We have various different clients that are going to interface directly with Container D, including the Kubernetes kubelet, the Docker engine, pouch containers, BuildKit, if you were in that talk earlier, uses the client. We also have a CLI tool, CTR. All of those kind of will use our Go Container D client to actually talk to the Container D daemon. And then we have a bunch of all of our composable parts inside the daemon. So I'm going to start talking about kind of the smart client design that we have first. So the Go client we have provides this higher level interface. So if you want to do something like a push or a pull, you can use the Go client to actually have the functions for doing the push or pull. The actual API that we have underneath it is much lower level. So if you want to use some of those, if you want the direct access to some of those lower level interfaces, you can get that through the client, but really the client is providing that higher level interface for doing the operations that you kind of expect to do with containers, such as starting a new container, pulling an image, all that kind of stuff. Also, for example, creating the OCI configurations, we actually do that in the client and allow Container D itself to pass through a lot of that logic. So the client, we have all these higher level operations, as well as like if you're coming in and you want to contribute to Container D, the client is actually a good place to start. That's where we like to accept new kind of functionality. If you come in, you want to build something, the client tends to be a good place to do that. The server is a little bit more kind of slow moving or stable, so it's a gRPC API. We've guaranteed kind of the compatibility with 1.x, so when 1.3 releases, any client that was using 1.2 before should still work. Also, that's where we have the lower level access to all our different components. So if you want to access the snapshotters or the content store, tasks or containers directly, you can do that over our gRPC API directly. So we also have the CRI plugin for Kubernetes. This is implemented, CRI is just a gRPC API. So the plugin itself is a gRPC plugin in Container D, and then it uses the Container D client directly, but it's actually inside of our daemon, so it will talk directly to our backend services. And so we'll talk a little bit more about that later. We also have Prometheus metrics. So we have a metrics API that will collect stats on a per container basis, as well as across the whole Container D process. So you can expose it through our Container D config. You just can specify the address you want the Prometheus metrics API to listen on and connect Prometheus there. And then the overall backend that we have for Container D, it's very service oriented. We have all these service interfaces for accessing. So we have interfaces for like snapshotter, task management, container management, even doing getting stuff like operations. We have like a diff operation in order to unpack your snapshots. So all that has a service interface on top of it, and then underneath it we have all our implementations. So the metadata store in Container D it handles everything related to namespacing. So images, containers, content, all of our labels are all namespaced. And what this really allows for is if you have multiple clients of Container D, whether that's Kubernetes or Docker or BuildKit or any of these different clients, they can all share the same instance of Container D without kind of overriding each other's name or overriding each other's resources. So it kind of isolates all the different resources in a single Bolt database that we have. And then underneath it, we'll have the different, we'll have the raw storage that will manage the actual bits. So for example, the snapshotter is one of these lower level components where the snapshotter itself is handling all the file system operations. So that's going to provide the copy on write file systems. This could be kind of a union file system like overlayFS or AUFS, or kind of a block device such as device mapper, or something like ButterFS, which is kind of in between. So the snapshotters actually hold the unpacked file systems. So you can think of them as similar to Docker's graph drivers today. The graph drivers actually store the unpacked layers for each of the images. So the snapshotters are handling that, but they're also handling whenever you create a new container, there's always a top level read-write layer that's going to be handled by the snapshotters as well. And lower down, we also have the runtime. So in In 1.2, this is when we released our V2 runtime, and this is we stabilized our Shim API. So when I mentioned earlier about having this first-class support for VM runtimes, you can see how we have all these different implementations of runtimes underneath Containerd. So runc is one implementation, but we also have run8cs that the team at Microsoft's working on, Kata containers, Firecracker. If you went to the talk 2 days ago, there's a good talk explaining kind of about Firecracker and how it integrates with Containerd. gVisor, which you'll also hear about more later. And all of those implement our Shim API, and they use this protocol called TTRPC, which I think stands for teeny tiny RPC. It's basically gRPC, but with optimized for just using over a socket with much less memory overhead. Because the Shim itself, you're going to have a Shim per container. So we've tried to really minimize what the overhead of that Shim is for doing container management. So if you're kind of working on one of these runtimes, or you want to play around with building your own runtime, you can have a look at the Shim API for how to implement that. So Containerd has a few different spots where you can do plugins today. The CRI plugin is actually just a gRPC plugin. The Firecracker folks are actually using a gRPC plugin as well in order to do some of their VM management. You can register any gRPC service on Containerd's socket that it listens on. For snapshotters, you can import any snapshotter that implements our snapshotter interface. We also have this proxy plugin, which can be used in order to run an out-of-process snapshotter. And then, like I just mentioned with the Shim API, you can basically bring any runtime that you want in Containerd, you can use it. So for the snapshotter plugins, this is the interface that you have to implement. It's pretty lightweight in terms of the actual operations that need to be managed. So you prepare, the life cycle of a snapshot is normally you're going to prepare it either from a parent or no parent. You can make some operations on top of, you can mount the file system, you can make some changes, and then you can commit it. And then after it's committed, it can't be changed. But you can use it as a parent for another layer or another snapshot. So like by design, the snapshotter is designed to be pretty lightweight. Like there's no data operations. You don't send data in or out of it, such as a tar. The snapshotter is not responsible for doing any mounting, so any file system management doesn't have to be done by handling all those mounts, they don't have to actually be done by the snapshotter, which can be kind of a pain for figuring out when it's actually time to do the unmount. We have support for, after you commit, the snapshots are immutable, so you can trust after you're done making your changes and you commit it, that nothing else can come in and make alterations to that snapshot. We also have some new stuff around label support, which we didn't quite have in Docker graph drivers. So basically label support just allows you to pin any metadata that you need to the snapshotter. So it's a little bit more flexible in terms of if you're building on top of Containerd and you need to store some information about what's inside that snapshot or something about that snapshot that you need to use, you can just put that in a label and it's namespaced and just store it along with your snapshot ID. As well as enumeration. This seems like a small feature, but it's really important to be able to actually have visibility into what all the different snapshotters or what all the different snapshots you have in your system. And Containerd has some cool tools where you can actually see all your snapshots and how they're related to each other using that enumeration. So the proxy snapshotter is basically you can take an implementation of that interface. You can build it in an external, or just build it into a separate process. And you can run it, and then you can configure Containerd to just connect to it and use it without having to recompile Containerd at all. So this is what Firecracker was doing as well for their first implementation of their device mapper snapshotter. So instead of having to recompile containerd just to test out the snapshotter, it's just a separate process that they can iterate on and test with. And once it's validated, then we can consider it as a built-in plugin. And for the runtime plugins, they also have a interface to implement for doing task management. So this is essentially what the gRPC API is going to look like to implement the Shim. It's just going to be a binary that containerd will call out to, and then connect gRPC to this, or the TTRPC, but it's the same definition in order to use your custom Shim. So yeah, this API it's much lower level. It's for actually doing the management, more analogous to what run C would be doing directly. This also has support for actually using the single Shim for multiple containers. It's kind of mentioned that advantage for VM runtimes when you're using pods. Another point where you can also extend containerd quite a bit is in the actual client. So the client has kind of some built-in opinions for how to connect to a registry and stuff like that. But you as a client user, you can actually override pretty much anything within our client. So by default, the services are going to connect to gRPC and just talk to the containerd service. But you can override any individual service in order to either use a different implementation, or in the case where you're already a plugin running inside the daemon, you can actually talk to the services directly instead of over gRPC. That's what the CRI plugin is doing. And then we also have these remote options where you can basically customize anything about the poll operation. So you can use a completely different distribution protocol. You can handle the data that comes back from the registry in whichever way you want. It's fairly flexible. So I kind of went through all the kind of different aspects. You can see how they kind of fit together. So I'm going to talk a little bit about how the polling works in containerd. As I mentioned, like the poll itself is actually done on the client. It's not done within the containerd daemon. So containerd has its interface, and then it has the content store and the snapshotters that usually you'll use the version in the containerd daemon. But you can just use our poll flow, and the poll flow is going to start from the client. Only the client actually talks to the registry, so the containerd daemon isn't going to open up any connections to your registry. So that gives the client the flexibility to configure how that connection to the registry is actually done. So if you have a proxy in place, you can actually do that kind of per poll operation rather than having to continuously restart your daemon to try to manage that. So the client's always going to start out by going to the registry. It's going to get a manifest. The manifest that comes back, it's just going to put inside the content store, and then it's going to look at all the other parts that need to be fetched from the registry. It's going to go and it's going to fetch each individual layer and also store those in the content store. At that point, the client can prepare a new snapshot, and then it will use our diff service to actually apply each of the individual layers. So that diff service actually, or that request goes from the client to containerd to say, apply this diff. It's going to use this snapshot. Containerd will read that content. It's going to mount the snapshot, and then it's actually going to do the unpack and just return the result back to the client. So the flow is really that the client is going to pull from the registry, put it into containerd, and then containerd will be able to read it back from the content store and apply those layers back into the snapshotter. And then when it's done, the client will commit that snapshot, at which point that layer is done. Once all the layers have been completed, the client will just call a create image call back to containerd, and at that point the poll is done. You have your image and you can run it. push in Container D is actually vastly simplified. It never actually talks to a snapshotter. All it does is it goes to Container D. It fetches the image that's going to resolve back to a manifest digest. It's going to read that manifest, look at all the layers that are part of that image. It's going to read those layers from the content store, and it's just going to push it to the registry. After it's pushed the layers, it pushes the manifest, and that's it for the push flow. So there's nothing that needs to go to the snapshotter. There's nothing that gets created during the push flow. And just like the pull flow, all the interaction is directly from the client to the registry, which has the same advantages as I was mentioning about being able to configure that registry connection however you want. The run flow, so we have a few different actors in place here for when you do a run. So everything is always managed by the client. It's going to talk to Container D over gRPC still. In our metadata store, we'll have each of the containers. We'll have metadata for each of the containers, but it's really the task manager that's responsible for the actual running container. So the task manager is going to get the create call. It's going to manage all of these shims that get created for the containers. So when you actually do a create container, it's the Container D is going to call its task manager. The task manager is actually going to create this shim process, and that's going to call the binary that was compiled for this Container D shim. So that could be the run C shim, it could be gVisor, it could be Firecracker. But at that point, it's going to create this shim and then return back to the client with a container object. At that point, the client is going to talk using the task manager interface to create a task. That the task manager is going to talk to the shim over that TTRPC connection and actually start the container process. And then it's just going to return back success to the client. Normally what happens next, the client's just going to call a wait on that same interface. That wait is going to call over that TTRPC interface, and then it's just going to wait for the process to exit. After the process exits, you'll get an exit status that will get returned all the way back to the client. And then the client can go ahead and delete the task. The task manager can shut down that shim process that was started up to manage that container. And then the client's free to actually delete the container. At that point, it's mostly just deleting the metadata. In Container D, it doesn't actually have any running state on the operating system. So I'm going to take a kind of deeper look into how the metadata store works. So I kind of mentioned the metadata store. It has, it does this namespacing, and it doesn't just have like information about the namespaces. It actually has information about all the different resources that Container D is managing. So for example, images and containers are just metadata inside of that Bolt database. The content and snapshots actually have information inside the metadata store about labels, as well as like ownership within those namespaces. But then they'll also have kind of pointers to the underlying implementations that actually store the data on disk. So in this case, I'm kind of showing an example where you might have two containers. You might have an Alpine container. That Alpine container is just going to have a single layer. In Container D, that image is just going to point to an OCI manifest. That OCI manifest is going to have pointers to the OCI image, which is we also refer to as the image config, as well as a compressed tar layer. In Container D, we actually create a pointer after when the pull operation completes, we have a pointer that points from the config to where that image has actually been unpacked onto disk. So in this case, we actually have the OCI image object in the content store pointing directly at a snapshot. Now, in this case, we have a Redis image as well, which has its own manifest. It has its own config, but it's actually sharing a layer with Alpine. So this would be the case where you have a Redis image that's built from Alpine, and they're going to share that kind of Alpine-based layer, and then you're going to have a Redis Alpine layer on top of it, which will just have all the installation for Redis. And then a Redis container that gets created that's going to have its own read-write layer in the snapshotter, and the parent of that is just going to be that Redis Alpine snapshot. So in Containerd, we have a garbage collection process that will run when images are deleted or containers get deleted. So in this case, if we went ahead and deleted the Redis image, all that looks like from a client perspective is that image getting deleted, but nothing else needs to get deleted at that point. Just that image will get deleted. And then when the garbage collector actually runs, these content objects that are no longer used will get marked for deletion. So since there's no more link between that image and that manifest will get deleted, and anything that that manifest was pointing to and nothing else is pointing to goes ahead and gets deleted. So after the garbage collection runs, you just end up with kind of this clean state of kind of as you'd expect. Anything that's not being used is actually get cleaned up from both the metadata store, and it will go ahead and clean everything up on disk that's not being used. Now likewise, when you go and delete that container object's going to get deleted, as well as that read-write layer that's no longer being used. And then when the garbage collection runs, it can actually go ahead and delete that unused snapshot as well. So the final state after doing that deletion of the image and then the container is just that you have your Alpine base image. So that's all I have to talk about for the kind of the architecture. We have Lantao up next. We're going to talk about CRI. So I can take a few questions maybe while we're switching.
Okay.
Hi everyone, I'm Lantao from Google Kubernetes team. I've been working in Kubernetes for 3.5 years and Containerd for 2 years, and I'm a maintainer of both of the project. And today I'm going to talk about the Kubernetes. I will give a quick status update of the Kubernetes Containerd integration, and also how Containerd is currently being used in GKE, the Google Kubernetes engine. And here is the agenda today. So first, let's quickly review what is Kubernetes CRI. CRI is the Container Runtime Interface. It's a gRPC interface defined in and a group of libraries defined in Kubernetes, and it defines all the functionalities we need from a container runtime. And ideally, any container runtime implement, the interface can integrate with Kubernetes. And it was introduced since Kubernetes 1.5. And after that, now there are several different container runtimes implemented this interface, including Containerd, CRI, Docker Shim, and a lot more. And the Docker Shim one is actually a CRI implementation built on top of the Docker API, because Docker itself doesn't implement CRI yet. And the Docker Shim is built in tree in Kubernetes today and still being used in upstream for testing. And then let's talk about how Containerd is integrated with Kubernetes, and it's through the CRI plugin. And the CRI is implemented in Containerd as a native plugin, and it was built in Containerd since 1.1, and it was GA since April last year, and we have massive test coverage in Kubernetes upstream. So if you come here, unfortunately today there is a failure introduced just yesterday. I already pinged the storage team about this. But anyway, we have all kinds of tests here. Each tab is a test suite, and each suite have hundreds of tests. So it should be reliable. Oh, yeah. And if we compare the Container integration with the previous Docker integration, we can easily figure out that the stack is simplified a lot, which usually means better performance and also stability. And here is the architecture of the CRI plugin. Basically, it handles the CRI requests from Kubernetes and use Container client to manage containers and images, and also use CNI to set up the network for pod. So that's just the high level description, and a lot of details are not mentioned there just for simplicity. And here's some performance data we got after we finished the integration. If compare it with Docker Shim, we use a benchmark with 105 pods per node, and after doing the benchmark, we can find that the new integration is better than the previous Docker Shim integration in terms of pod startup latency, CPU usage, and also memory usage. Yeah, and after switching to Container, we recommend users to use the new command line tool called CRI to debug their Kubernetes nodes. CRI is a command line tool built on top of CRI, and it should work across all the CRI runtimes, which includes Container and CRI, even Docker Shim. And it should provide the same experience. And we try to make it provide a more Kubernetes-friendly debugging experience. Here's an example. So if today you log into a Kubernetes node and run Docker PS, you will see a bunch of information like this, which includes a group of pods containers, which doesn't mean anything. And also the container name is super long because as Kubernetes, we don't know where to put our metadata, so we just put it into container names. So it barely means anything to you. So now with CRI, it will become something like this. If you run CRI pods, you will see all the pods on the node, and also CRI PS will show all the containers. It provides a much clearer debugging view, and yeah, should help you easily understand what's running on the node. And then how to switch from Docker Shim to CRI plugin? Actually, it's pretty simple because remember that Container is part of Docker. So actually, we're still using Docker. We just upgraded and change the configuration a little bit. So basically, just upgrade Docker to 1809 or higher, which already has the newest Container built in, and then set the CRI Container flag in Docker D. Then it will enable the CRI plugin. And the third step is to configure your Kubernetes to use Container. Basically, just those two flags. That's the most basic two flags you need. And after that, in your cluster, if you are not using CNI, then just install a CNI plugin. For example, Calico or Waveworks, and then it's done. You'll finish switching from Docker Shim to CRI plugin, and it will be like this. So previously it's from Docker Shim to Docker D, and now we're still using Docker, just using a different API inside Docker. Yeah, so that's about Kubernetes and Container. Basically, it's ready for production use. So just upgrade your Docker and change the configuration. And then I'm going to talk about how Container is being used in GKE today. GKE, Google Kubernetes Engine, is a hosted Kubernetes service provided by Google Cloud. And today we support two OS image types in GKE. One is called the Container Optimized OS. It's built and maintained by Google. It's based on Chromium OS. And another one is Ubuntu. It's maintained by Canonical today. And both of the images are providing Docker 17.03 today, which is a pretty old version. But that's the version evaluated in Kubernetes upstream test today. And to support Container D, we added a new image type called COS Container D. It's basically just a COS image, a variant of COS image with Container D installed. And to use it, you just need to create your cluster and specify this image type, and then you have a cluster with Container D as the container runtime. And the COS Container D image type was beta last November, and we plan to graduate to GA by the end of this quarter, hopefully. And then after COS Container D is GA, the next step for us is to switch Container D as the default runtime. And just as I described just now, our plan is the same. First, upgrade Docker to 1809, and we have already done that. It will be available since GKE 113, which is hopefully coming in May, maybe next week. I forgot the time, but in May. And then after that, at some point, we will switch to Container D, which is shipped with Docker. Switch to Container D as the default runtime, and after that, we will still keep a Docker shim option for a while during the switch, because some users may build their toolings around Docker today, and they may need some time to switch to Container D. So that's Container D support in GKE today. And then let's talk about something a little bit more interesting. Actually, after decided to switch to Container D in GKE, we already started to build some new features on top of Container D. And one of them is called GKE Sandbox. And the motivation is very simple. We all know that container can escape because Linux has a very large attack surface, and the application inside the container can exploit the Linux bugs and then to bypass the container mechanism or get higher privilege. And once they do that, they can probably get some important data from your node, or even from other containers, other users' containers. So this has happened before and may also happen again in the future. And this is especially bad if you are you're hosting some code that you're not familiar with. We call it untrusted code. For example, you're providing a function, you're providing a platform which provides function as a service. You run customers' function, but you don't know what they are doing. And maybe there's malicious code there you don't know. Or you're hosting customers' web service. Also, it's similar. You don't know what they are doing. And if they leverage the bug and break out the container, it's possible that they can go into your system, get some important data, either from you or from your other customers, which is very bad. So we want to try to avoid that. That's why we started the GKE Sandbox project. Basically, what we want to do is that we want to put your container into a sandbox instead of just running it on the host. So that even if the untrusted code inside the container escape from the container, there's still a second boundary, which is the sandbox can help you protect you from the untrusted code. And so basically add a second layer of defense. And currently we are focusing on gVisor, which Derek has just mentioned just now. And but actually other sandbox technologies can also be supported in the future. And I will firstly quickly introduce what is gVisor. It's a sandbox technology based on user space kernel. It's written in Go, and it was open sourced last year. It's OCI conformant, and just like all the other OCI runtimes, we have a name, run something, and we are called run SC. So run C is run container, run SC is maybe run secure container. I'm not sure, but they name it in this way. And so this is gVisor. And and to help you understand, we can compare gVisor with some other sandbox technologies. The first one is we call it machine-level virtualization, basically just a VM. The second one is rule-based execution, basically all the existing Linux security mechanism, including seccomp, SE Linux, IPARMA. What they do is that you can set some rules to your application to make sure it only does what you expect it to do instead of doing something else, which may break your system. And gVisor is different from the previous two in that it runs a gVisor kernel in the user space, and you run your application on top of that gVisor kernel. And under the gVisor kernel, they use existing Linux security mechanism such as seccomp to filter the syscalls. And each of this approach has pros and cons. For example, the first one, the VM-based solution, the good thing that it's very simple because you don't need to configure anything. Just put your application in a VM and run it's secure. And it's good, but on the other side, the potential, the bad thing that it may take more resource. It means that it has higher footprint and also longer startup time. And also you can now usually lower density on the node. And the second one, rule-based execution. The good thing that it has very high performance because it just you just run your application on the host kernel. You just add some rules to make it secure to reduce the attack surface. But the bad thing that firstly that you need to understand all those security technologies very well, and also you really need to customize the rule for your application. You have to understand it very well, know what it will do, then you can apply the rule. So for example, for the use case I mentioned just now, if you are providing a function as a service, you don't even know what the application will do, then it's very hard to apply a generic rule for all the code. And gVisor, the good thing that is just as similar with VM, you just run your application in gVisor and it's secure. And another good thing that is, in theory, it should be more lightweight and start faster and have higher density because it only run a reduced user space kernel instead of the whole VM. But the bad thing is that if your application uses syscall a lot, it may be slow because the syscall support of gVisor goes through a user space kernel. It might be slow. So anyway, this is just gave you some basic concept of what is gVisor. And now, to support gVisor in GKE, the first thing we need to do is to be able to start it in Container and to start and manage it. And gVisor is different from runC. So the picture above is runC. So basically, although the application is containerized, but it's still run on your host kernel. So you can send signal to it, receive signal from it, or check signal to get stats, or access its terminal. So basically, it's on the same kernel. Everything is simple. But for gVisor, as I said, gVisor has its own kernel. So you cannot do things like what you do to runC. You have to talk with gVisor kernel to do all those stuff. So we need, to handle this in Container, we need an abstraction layer in Container to inject different logic. And so when we started trying to do this, we basically revealed all the layer that we can plug in different logic. And we found that if the abstraction level is too high, then it means that we need, for example, if it's as high as CRI, then we basically need to re-implement the whole stack. But if it's too low, as low as the runC CRI, it's already proved that something doesn't work. For example, signals that because Runc is different with gVisor is different with Runc, we cannot do things exactly the same. And after some investigation, we found that the Container Shim interface is actually just right for the use case. It's not too high or too low. It contains everything we need. So then we worked with the Container community to propose the Shim V2, which is almost the same with previous Shim API. The only difference is that we make sure that, for example, queue and wait is in the interface so that we can handle signal. We can implement the signal handling under the interface instead of let Container do that directly. And also stats is here, and also resize the terminal thing, exact thing. So basically, just hide all those details under the interface. So after that, we implemented the Container Shim for gVisor. It's open source, and after this is done, now you can use a single Container, but start either Runc container or gVisor container. And now actually it's a standard now. All the runtimes now integrate with Container in this way, and Derek has already mentioned. And that's to support gVisor in Container. And now, after that, we need to provide an API in Kubernetes for user to be able to say that I want to create a pod and I want to run this pod in gVisor. So we introduced the runtime class API inside Kubernetes. So basically, you can define a runtime class, and in the runtime class object, you can see how the runtime should be configured and what the low-level runtime handler to use. And for gVisor, it will be something like this. And if you use GKE Sandbox, it will be automatically installed in your cluster. And then after that, when run a pod, you can say, please use the gVisor runtime class to run my pod. And then that's it. From API, Kubernetes API perspective, that's it. And then we need to support runtime class in the CRI. And we added a new field called runtime handler in the CRI interface. Basically, when Kubernetes try to create a pod, it also tell the underlying runtime what the runtime handler should be. And for gVisor, the runtime handler is called gVisor. And then lastly, in Container D, we added the config support to configure that for each different runtime handler what underlying shim you should use. And for gVisor, it will be like this. And also, this is automatically configured in your GKE cluster if you're using GKE Sandbox. And basically, from high level, when user create a pod, it says that I want to run this pod in gVisor. So it specifies the runtime class gVisor. And then when Kubernetes create a pod, it tells Container D, please run this pod in with the runtime handler gVisor. Basically, run it in gVisor. And Container D is configured to run the config that if you try to use gVisor runtime handler, then use the rise the underlying shim. Then Container D start the corresponding shim, and then the shim knows how to understand all the config and how to start gVisor container. So that's basically how it works. And also the same approach can be used to all the other runtimes, including Kata and probably Firecracker. So GKE Sandbox was alpha last September, and the beta is coming soon. Hopefully next week, and I hope it's not delayed. But anyway, it's coming soon. And to use this, basically just run this command against your GKE cluster to create a node pool which has gVisor support. So two important flags. One is the image type I mentioned. You need to use Container D image because the whole thing is built on top of Container D. And the second thing is that specify the sandbox type to be gVisor. And I have a quick demo. I recorded it before instead of live demo. Sorry. Oh, is it too small? Yeah, so I have two node pool. Node pool is a GKE specific concept, basically just a pool of nodes. And I have two node pools in this GKE cluster. One is the default one, and another one is a gVisor one, which has the flag I mentioned, the sandbox type flag. And if we get a node, we can see that because in my demo, each node pool only has one node, so there are only two nodes. One belongs to the default pool, another one belongs to the gVisor pool. And we can see that both of them are Container node, and the Container version is 1.2.6. The second one is the gVisor node. And now, oh, so slow. And we can check that the gVisor runtime class is already installed there. And now I have two pods, two deployments. The first one is a gVisor one. You can see we specify the runtime class name equal gVisor at the end. And another pod is just another deployment is just a regular deployment without the runtime class name. So ideally, the first pod will be running in gVisor, and the second one will just be running as a regular container. And let's create them. So create the first pod and then create the second one. And both of them are running now. And what I'm going to do is to exec into the pod and run dmessage. Dmessage basically show you the kernel log, show you the Linux kernel log. And for gVisor, because I said that you're running on your own gVisor kernel instead of the host kernel, you should see the logs from gVisor. And for the regular one, actually, because you're using the host kernel, you should see the log from the host kernel. Usually, it's a lot of logs. And this is the gVisor pod. You can see that you see the gVisor kernel, some starting gVisor, and we're ready, something like that. Means it's running inside gVisor sandbox. And and for the regular pod, if we do the same thing, you will see a lot of things. That's from the host. I don't understand any of them. Yeah, but it's from the host. And if we now if we SSH into the gVisor node, we can check that the first one is that we did config the gVisor runtime handler to handle gVisor pod, and also just to prove that it's running Container. If we run CRI version, you will see that this is the runtime name is Container, the version is 1.2.6. And also if you run CRI inspect, so now if we list all the pods and inspect the gVisor pod, you will see that it's it will tell you that it's using gVisor. So if we inspect it and grep the runtime field, you will see that the runtime handler is gVisor. So now you have your. So now if you have untrusted code, you don't trust, but you do want to run it because maybe it's your customer's code, then you can consider running it inside a sandbox, for example, gVisor sandbox, and then you won't worry about it break out the container and then damage your system or steal your data. Yeah, I think that's the demo. And just a quick recap. First thing that Kubernetes Container integration is GA now, and feel free to use it in your production. Just upgrade Docker and change the config. The second thing that the GKE Container support is beta, and we do plan to make it default sometime soon. And the third thing that the GKE sandbox is built on top of Kubernetes plus Container plus gVisor. And the last thing is Container is super powerful. you can see that there are so many layers of interface you can plug in different logic. And Derek also mentioned that for image management, actually there are also different interfaces. And we do plan to do something for image thing too. So if we've done that, I will probably introduce that in my future talks. So here are some links, the CRI plugins repo and information about GKE Container D and information about GKE Sandbox. That's it.
Yeah, so I believe we're going to have a panel discussion, or are you saying something first, Phil? Are you doing something first? Okay.
We'll do the maintainers. I just didn't know.
Cool. Yeah, were there any questions for Lantao while Phil gets set up? No questions? You're going to make me do like a song and like a jig here? All right, well, we'll just watch the clock while Phil gets ready. No pressure, Phil. Yes.
I have a question about the Shim V2 with regards to sandboxing. So whenever you have the sandboxing stuff, you talked about the semantic gap between what the process is and what the process is in the sandbox, right? So certain things like memory stats. How do you calculate that? Like, is it what's being used by the user space kernel plus what's being used by the process, which is being p-traced, or is the information that you're getting out going to be the same, or is it going to be different in some sense?
Yeah, sure.
Yeah, like memory stats, because like usually if you're looking for memory stats of a container, you just ask the kernel, right? Then the Linux kernel keeps track of the pages both in user space and kernel space. But when you have a sandbox, because of the semantic gap, you have to calculate the pages within the kernel as well. But then it's a bit complicated because you have this level of abstraction that you have to keep track of.
For gVisor, so for Kubernetes we have pod and container, right? And for gVisor, actually, although it's a sandbox, but it's a much simpler one that is just several processes. So you can just put it into the pod C group. So for each pod we have a C group, and so from the C group you can still get all the stats data you need.
Okay, so you do it it's per pod, so you just
yeah, it's per pod. For each pod we have a sandbox, and you can get the stats. But for container stats, currently gVisor doesn't support C groups inside the sandbox. So
yeah, that does. Yeah,
so hopefully in the future it will provide more stats for containers inside the sandbox. But for the sandbox itself, including everything inside, you can get all the stats from the C group outside.
All right, great.
Yeah.
Thank you.
Yeah.
Thank you, Lantao. Next up, we have Phil from IBM, Phil Estes.
All right. Well, thanks for sticking around. I know we're getting at the very, very end of your ability to stay at a conference, so thanks for hanging around. I'm going to wrap up hopefully that flow made sense, that you've kind of seen the architecture, so I'm not going to dig any more into Container D. You've seen how the CRI sits on top of that, enables Kubernetes to use Container D, and how Google is using that. So I'm just going to stick with more, as another public cloud provider, how we've adopted Container D and migrated from our original use of Docker and the Docker Shim. So I've been maintaining in the open source world Docker Engine for several years with a lot of these same folks. Helped with Container D the last few years. And my connection point into our cloud is then helping our product side determine how to use the open source that we use, Kubernetes, Docker, Container D, et cetera, and making that linkage for how we offer that upstream. So a very brief history on IBM Cloud. You may have heard of it more referred to as Bluemix over the years, and that's because we originally, after acquiring SoftLayer, built out a platform as a service called Cloud Foundry. It was called Bluemix. And then around 2015, we got very involved in the Docker project and offered a very early container API service around the Docker API. And then the year after that, got involved in serverless and created an open source project called OpenWhisk that used Docker as the invoker. So when you submitted a function, it was actually a Docker container that would run. And then, like all the other public clouds, moved into Kubernetes around that time, and in 2017 offered something we now call IKS. So again, a lot of this has kind of drawn us into Docker in the container world, and has created a set of dependencies over those years on open source technology. Many of those obviously involving the Docker CE engine, Docker distribution to build out a registry, Notary, and Tough, and the Docker Content Trust. We added that to our registry. Even our Cloud Foundry service, so that runtime remains in our cloud. And if you've watched the Cloud Foundry world, they first rebased on runc when the OCI came out and are now using Containerd as well. And there's even a version of Cloud Foundry that was announced this year that uses Kubernetes to run its control plane. And then we also have an on-prem Kubernetes that, again, is built around open source. So again, you know, our choice at IBM has been to always get involved in these projects that we depend on. And so over the years, I went out and found, you know, everyone that's committed to the Docker repos, to Docker distribution, to runc, to Containerd. And you know, over the last few years, we've had about 77 different people contribute, again, enabling hopefully this technology, not just for us, but for many different people. And of course, all these people don't still work for IBM. I think there's someone in the audience here whose picture is on the screen who is no longer with us. But again, we definitely prioritize giving back to these projects. So as I'm involved in Containerd, I think this mic is slowly going out. I hear it coming and going. So if that gets annoying, I can switch. Or I can even use this mic if that helps. So as I got involved in the Containerd project, and as you saw from Lantao's presentation, you know, one of the things that attracted us operationally to Containerd was simplifying this picture. Simplifying this picture and having a simpler operational model for how we ran containers in our Kubernetes offering. And so this is really just a different variant of a picture that Lantao has already showed you. Moving to Containerd, where you have the CRI plugin built in, not having the Docker Shim, not having the Docker engine, simplified that architecture, less memory use, less CPU overhead, and so effectively that was a valuable move for us operationally. The challenges, of course, as you move your Kubernetes clusters off of something that people have sort of been accustomed to, is that you find out that people haven't always kept to the Kubernetes abstractions. You have people that still have dependence on the Docker API socket. For example, we have a lot of integrations in our cloud, like I'm sure every public cloud provider has, with Datadog or Sysdig or other tools or storage drivers. And many of those tools and those vendors' projects were depending on the Docker API. And so for about the last year, we've been working with each of our vendors to help them add Containerd support or finding a different layer of the stack, you know, OCI, runc, to integrate their tooling. And the second was not really a regular occurrence, but obviously as Containerd is a new code base and drop kind of Docker's opinionated approach, even though the CRI plugin tries to mimic that Docker Shim behavior, you know, we found certain private registries that didn't follow the V2 API implementation properly. And so you can look back at the Containerd merge PRs and see lots of fixes over the last year for different ways that people expected a certain behavior, or we've helped upstream other projects correctly implement those behaviors to fix those problems. So again, we've spent probably the last 12 to 18 months slowly migrating to Containerd and not using the Docker engine again in our Kubernetes clusters. And so obviously a couple benefits for us. I've already, Lantao's already showed you some performance graphs about memory and CPU use between Docker Shim and CRI Containerd. For us, there was also some operational improvements. We had added some extra checking, so in older Docker versions, there could be, under significant load, some fighting between Dockerd's view of Containerd's health, killing the process, trying to restart it. And so we had added some operational health checking to try and keep that working in our production clusters. Not having Dockerd and Containerd both there obviously allowed us to simplify that. And then there's a reasonable increase in per node scalability because of what Lantao showed you, being able to fit more pods per node on the same hardware configuration, finding CPU and memory use decrease per container. And some of that's, Derek showed you the TTRPC, so that was done specifically so the per container shim was using less memory. And so again, we've seen those benefits practically in reality in our service. So where we are today with the IBM Kubernetes service, we have 77% of our production clusters now are using Containerd. Part of that is because people creating new clusters today in the Cloud Console defaults to Containerd. So kind of like Lantao, Google is on that same path. For us as well, for a while it was a choice to pick Containerd. Now we actually put this note here, so if you're using the command line interface to our Cloud API, it tells you clusters at versions 1.11 or later running Containerd instead of Docker. And because we no longer support creating clusters with version 110, that means every cluster you create in IBM Cloud is now using Containerd as the runtime. And I've simplified a get nodes output here just to show that, again, on my particular cluster that I was pointing at, it's 113 Kubernetes upstream with Containerd 1.2.5. And I think if I did what I was supposed to do and click the update button, I would get 126, the latest version of Containerd. Also, I mentioned IBM Cloud Functions. So this is built around the Apache OpenWhisp project. Was using Docker as the invoker for functions. And so they've been on the same path of migrating to Containerd because they sit on top of our IBM Kubernetes service. Their control plane is run on Kubernetes. So about 2 weeks ago, they finally started to move some of their clusters onto Containerd. And again, a couple quotes from the team. Simplicity of the API, they're able to adopt Containerd quickly and easily. Again, in a functions environment, performance is critically important to them. And so again, having the ability to have container operations be reliable, highly performant is very important to them. So again, outcomes for us, better stability and performance on the cloud functions side. A few stats that they gave me just in the last week as they're running in production, many operations per second per node with very low error rates and no performance degradation, so they're very happy running on Containerd. And then both our public cloud, the IKS service, as well as our cloud private are seeing this simplicity in an operational sense of not managing, laying down Docker and Containerd and managing that stack together and seeing some incremental performance improvements with memory and CPU, as I mentioned. again, there's not, it's, as Lantao showed you in his demo, many things obviously look the same, whether you're using Containerd or not. I have a couple clusters in IBM Cloud, and this is the difficulty of naming something after a version. My K8s 1.1_11 is now running Kubernetes 1.12, but oh well. So I can do that, but maybe why don't you take this mic back and just see if there are any questions, and I can, here's my live Cloud Console with my clusters. You can obviously see, again, this is the same you saw in the, oh, you've got one, the same you saw in the capture of my command line, 113. I've got a 3-node cluster. And we also have some new capabilities. You can add Istio to that, or Knative. There's a beta terminal feature. But again, I can show anything anyone's interested in, but maybe it'd be better use of time. I know people are getting a little conference weary if there's any questions. And then I think we're going to do kind of an open ask the maintainers as well. So, any specific questions about our adoption of Containerd? Otherwise, we can.
Well, I have a question.
Yes.
How did you deal with dependence on the Docker API socket?
Yeah, like I said, that's not like it's not an issue you kind of like come to the end of. So we did a lot of production scanning of like just finding people that are running pods with mounts of var libdocker.sock. Found out is that because they're using a product that depends on that is, so basically trying to create a spreadsheet of like who's using the Docker socket and why. And we found almost all of it fit into two categories. One is add-ons like Sysdig, like other tech tools and technologies, Twistlock, Aqua. So this is like a year ago. All those companies, all our tier 1 integrations support Containerd out of the box now. The second bucket is people doing in-cluster build using Docker build. And so I'm, plenty of great information out there about using Knative build or BuildKit. And so I'm writing a blog post again with a simple example of showing how you don't need Docker to do in-cluster build anymore, the Docker daemon. But yeah, but there's always outliers, who else is depending on the API and helping document and inform how to get rid of that dependency.
Any other questions? Cool. So I guess we're going to have like a little panel discussion thingy here with the maintainers. Panel discussion.
Here we have this as well.
I think we can just sit down here. So this was less of a specific topic that we have for the panel discussion. It's more kind of ask us anything about Containerd. We have different maintainers that own kind of the different levels, including Michael.
Hello. I have a question. I was wondering if you could talk about the Containerd integration into Moby. See that there's a big piece of work going on, long-lived branch. There's a lot of work that needs to be done, and how people can get involved as well.
Yeah, we have an ongoing integration into Moby. There's a branch right now. We have a draft PR. So the first version of this integration is mostly focused on replacing Docker's storage So like all the image storage, all of the distribution to use Containerd's code. Right now there's some duplication and functionality. Docker engine handles all the pull push stuff in its own way. It has its own way of storing images and containers and all that stuff. So we're working on just replacing all of that with using the Containerd client and then using all of Containerd's functionality for doing push and pull. So that's like 90% complete, but that 10% is we'll see when that gets done. But that's all stuff that's ongoing right now, and I think what you'll expect to see after that is the case where you can just run Docker on top of Containerd, and it can manage containers by anybody who's using that's using Containerd, any of those clients. You can use Docker as your kind of tooling for listing your containers, managing, even polling. So basically, you'll see much better use of the Docker CLI in order to do stuff on top of Containerd.
It was mentioned that IBM's function as a service is running on Containerd. Actually, for Google, do we have any timeline on when we can see Google Cloud Function as a Service offering running on Containerd, or is it already?
Actually, I'm not sure how Cloud Function. Google does have Cloud Function, but I'm not sure how it runs. I guess it's now running on GKE, so I'm not sure about their architecture. Yeah, so in the recent Google Next, we announced a thing called Cloud Run. I don't know whether you know about it. It's our version of serverless, which combines function as a service and container as a service. So basically, you can run a container, provide a container image, and we can run the container for you, and we handle the scaling up and scaling down based on traffic. And if there's no traffic, we scale it down to 0. When there's traffic, we scale up crazily. So basically, like function that we scale up and down to 0, but like container because you can just provide a container image. And that thing is called Cloud Run. And Cloud Run has two modes. One is Cloud Run on GKE, which is that you can use the same API, but on the backend is your GKE cluster runs Knative. Of course, you can support Containerd there because it's just a GKE cluster. And another mode is the regular Cloud Run. It's actually running in the Google infrastructure on the backend, and that thing is using gVisor now, just like the previous app engine. But now that one, I'm not sure when it's going to move to GKE but as long as it moves to GA, it will be used Containerd.
Yeah.
When I run gVisor and GKE, does it use ptrace or KVM in the backend?
Yeah, in GKE, actually you can just create a GKE sandbox cluster and see. It's in the config file. There's no secret. It's in the config file. We are using a different platform called Xemu, XEMU, and it's actually open sourced. If you just go to the node and search around, you will find the source code. So, but I'm not an expert of the too low level of gVisor, but that one should be faster than ptrace. Yeah.
I have a question about just like plugins in general. Is there any plans to make plugins so that we don't have to at least modify a bit of the Containerd code for the more generic plugins, they want to hook something into image fetch or something. So this is like the CRI plugins, stuff like that.
Sorry.
Like, so basically like a more generic plugin, like not specifically about Snapshot or I mean, we have that to some degree.
I mean, is the case that you're talking about where we have a lot of client extensibility, but the CRI implementation is actually is a client itself. So any sort of plugins need to be defined by CRI.
Sorry, I didn't follow the question. Sorry.
So basically, like if you wanted to replace anything around like distribution in CRI, you can do that if you're using the client directly. But if you're using CRI, you're using a different interface. You're not using Containerd's client directly. So the question is there plans to make CRI itself more pluggable for stuff that's pluggable in Containerd's client?
Oh, okay. So I feel like CRI is pretty simple. Just it includes the runtime part. We call it runtime service, and the image part we call it the image service. So I don't know how to make it more pluggable. Do you mean that you want to make a specific function to have a different implementation, and other functions use the previous implementation, or?
So we have a kind of like a really specific use case, I guess. So so this is around the encrypted images work, and one thing that we are trying to do is we want to inject keys into. So like we don't, in certain scenarios, we don't trust the Kubernetes secrets engine. So we want to inject keys directly from the host. So we're trying to hook into the CRI flow to inject those secrets from the host instead of through Kubernetes.
I see.
Yeah.
I think in CRI, today, our way of extending CRI is to use annotation.
Okay.
I mean, it's bad, but but that's how people do it. Usually people start with defining some special annotation, which means, put their secret API there and then handle it in the actual implementation. And then after a while, when all the people agree on that, this annotation is actually useful, we graduate to an official API. And for the image thing, actually today, I don't think we provide any way to inject annotation or extend the image spec when you pull image. So if you want that, you can propose it in the community. I think it, at least for now, I think it makes sense to me.
Okay.
Yeah.
Thank you.
Any other questions? Any pull requests you want to hit them about?
Does that mean you get a closeout DockerCon here, Brian?
Maybe.
You're going to do Moby Cool Hacks here, right?
Yes, Moby Cool Hacks. User namespaces by default. No, it's a thing. I have a PR. I'm not joking.
I've seen it.
All right, then. I guess we are adjourned.
All right, thank you, everybody.
Thanks.